stop because I'm going to go through loads of examples. O2, O2 excited state, N2, N2 excited state, N2 minus, N2 plus, F2, F2 excited state. So I want to go through all of these examples, and that's where I'm going to do that in a part B video. Okay, but one last term symbol operation to describe, and this is for when spin orbit splitting must be taken into an account, which is going to be predominantly for doublet states. And what hopefully you recognize right now, doublet states are often free radicals, right? Because a doublet state is one unpaired electron, and it's a doublet because it can be up or down. Okay, so let's go through this NO example. I want to make sure I have it in front of me so I get it right. Okay, and so first I'm going to put together the full term. Okay, so if we walk through, so here we can see that oxygen is more electronegative than nitrogen. And so I think I missed describing that on the heteronuclear diaterms, but one way we know which one is going to be lower is the more electronegative element is always lower in energy because it requires more ionization energy, right? Because remember, in this MO diagram, you know, ionization is up here at the top. That's our reference frame, okay? So here we've got the NO electron configuration, and we can see that it is a radical, right? NO is one unpaired electron. So let's see. So we know that the two sigmas are going to wash out to be 0. We know that all of these bonding electrons are going to wash out to be 0, right? 0 plus 0, and -1 and -1 and +1 and +1. Those are all going to turn out to be 0. But now we've got one electron in the X. I can call that -1 or +1. It doesn't matter because of the absolute value. So that's my only lambda value, right? So that's going to be a pi state, okay? And hopefully I recognize that it's got to be a doublet because it's one unpaired electron. And so now we're not so concerned here with noting if it's G or U symmetry, because with doublet states, what's more important is to take into account its spin orbit splitting. And so that is given by this omega, which is analogous to J for atoms, okay? And so omega is going to take on all values lambda plus S, all the way down to lambda minus S. I missed that. Or rather, because S can be plus or minus 1, right, what ends up happening is we're going to get two possible J values, just two possible, I can't talk, two possible omega values, just like we see two possible J values, right? There's the high J and the low J. We're going to have the high omega and the low omega, okay? And so here, if lambda is equal to 1, remember, we only want the positive value, then that means this omega for NO is going to be 3/2 or the doublet pi 1/2, okay? And so as it turns out that the doublet pi 1/2 is lower in energy for NO, so that creates its ground state. However, if we flipped the spin on that electron, that would make it the doublet pi 3/2 state, which would be an excited state. It would be slightly higher in energy, and it would be an excited state, okay? Which is kind of cool. All right, so now, like I said, in the next video, I'm going to walk through these examples, but I want to record that as a separate video because I've already been going for about 35 minutes. Okay, folks, so make sure that you follow me through these videos. And like I said, I would recommend, working with these empty MO diagrams, drawing them for yourselves, or, using these blank MO diagrams that I have right here. And you might even try going through all of these yourselves before watching my video. Okay? All right, folks. Happy term symboling.